So, for the AI era facilities, thermal challenges are proving to be just as demanding as electrical ones. So, joining us now today is Paul Quigley, President and Chief Strategic Relations Officer at AirSys Cooling Technologies. Paul brings a very unique strategic and operational perspective to what arguably is the most rapidly evolving sector of our industry. So, Paul, thank you so much for today, and the floor is yours.
Oh, it's my pleasure. And boy, what a joy listening to Sayeri, right? I mean, I always learn
She's
so
great.
much. Sometimes I go into a conversation trying not to learn something, but with her, I'm always gaining more information. So it's wonderful. That was a great
Likewise.
job. Yeah,
Perfect.
I think what's important for us to talk about today would be really the moving from the discussion of just power into the discussion of power to compute and how they're interlocked together. So I'm going to walk through a shift happening in our industry, and it's not incremental shifts, but they are actual structural ones. So as we're seeing in daily news, daily headlines, we're moving from a world where power used to be assumed to a world where power now determines everything. And more importantly, it's not just how much power we have or even how efficiently the infrastructure might be designed. It's how that power is actually allocated. So I think as we were just discussing in the last session, for over a decade, most of the industry has thought of the site selection as a weighted scoring model, more or less. And I think too many in the industry still do. So traditional measures, they've always considered, power gets 30 to 40%, fiber gets 20% of the consideration, and then regulation, water, and land, they've always filled in the remaining portion. And honestly, that model actually worked very well before 2020, before AI, before the high density GPUs began emerging and HPC became the standard. But today, today that model, I'm going to say it fails. Today, sites pass that model, but they never get built or they never get financed. And the reason behind that is basically because the site selection is no longer parallel scoring. Today, the site selection is more of a sequential filter. And basically what that means is that if you fail at the top of it, nothing else matters. So to be clear, I mean the five constraints didn't change, but what has dynamically changed is the order and the impact. It's unavoidable. So, kind of taking a brief step back in all of this, before 2020, the data centers were a real estate problem. Location selection was a consideration, and connectivity mattered most. Power was a consideration prior to 2020, but kind of more of a checkbox and an assumed thing, more or less a given. And then AI arrived and changed everything dramatically. The scale increased dramatically, and I'd almost propose that it was unexpectedly. We had been warned about AI 5, 10 years prior, but there was no revelation of it and really no direct impact. But then suddenly everything changed. And so where we find ourselves today, what are the headlines focused on? Delays, permit struggles, and now we're seeing community outrage. So the interconnection timelines, as we were just discussing, they've increased dramatically to a point where we can't even support them anymore. The backlog, it now exceeds the installed capacity. And then the real issue is the stability of the struggle. This is not temporary. It's structural. It's very significant that way. And it's more than just an inconvenience. It's, in my opinion, it's pragmatically detrimental. The outcome has a real threat of finality here, and not the kind that the market was ready for or prepared for. I would say, to the point where if interconnection timeline exceeds project timeline, then that site is basically dead. Literally everything else becomes irrelevant. So we had talked about that the site selection's no longer a parallel type scoring anymore. It's rather that site selection has become sequential filter, and power determines the viability. Everything else follows that, or it doesn't, period. Even behind the meter power is not being aggressively challenged or is now being aggressively challenged in communities all over the globe, and the fervor is being dynamically amplified on social media. So, in a sense, the communities are joining the power grab in a way. And make no mistake, that impact has been significant. Here in the United States, almost 30% of the planned data centers have been stalled or even canceled due to community resistance. So really, the industry response, it's been consistent, unfortunately. Still just trying to add more power, focused primarily, if not solely, on building new sites, waiting in queues that are beginning to look circular almost rather than linear. Lines up for power that really never seem to find the power, and projects that are being canceled at the last minute. And then we see this a lot in the UK, where the line starts all over again and the bureaucracy gets involved, and the permitting can extend it another 3 years beyond the power capacity problem. And the fact is that many facilities, they have provision power, and the problem is not enough of it's allocated to compute, which is the entire reason for the power in the first place. So the opportunity is in refocusing what we want by reevaluating what we have. And the issue is not supply so much as the issue is truly allocation. So if we take a quick look at, the traditional metrics of evaluating how effectively our existing data centers provision the power that they already have, I think it's important to review PUE. PUE, for those who aren't completely familiar with it, and I think most are, it stands for the power usage effectiveness, but it's most commonly referred to as power usage efficiency, I think. PUE has been and still is the most commonly used metric in the data center industry. So PUE, what it does is it basically compares total facility power to the portion used by the IT equipment. And so in simple terms, I mean, how much extra power is required to support the computing load. And the formula is consistent and stable, and it's still informative. PUE is still a good metric for us. PUE is basically the total facility power divided by the IT equipment power. I'll give you a real quick kind of a visual example of that. So a PUE of 2.0 would mean for every 1 megawatt used by the servers, another megawatt is used by cooling losses and facility systems. A lower PUE has always meant less overhead, more efficient operation. But here's the limitation of it. So PUE measures efficiency of power usage, but it does not actually measure how the power is allocated within the facility. And that distinction is not only important, it's revealing, and it's becoming extremely apparent in the industry now that AI is the dominant factor. So while PUE will tell you how well the system runs, it does not and cannot and was not designed to tell you how much of your available power can actually be used for compute. It just simply wasn't designed to do that. In fact, there's no current metric that actually measures allocation. All the current metrics, and they're all very strong in their own sense. So the current metrics measure performance. The PUE and DCIE, they both measure efficiency. Good things to know, very important. IUE, very promising, and gives us a really clear view of the actual and verifiable output, the compute output, which is what we're all after. That's the whole point of everything. CUE, WUE, those provide us with really critical valuations related to the environmental impact. But there isn't a current metric out there right now that measures how power is allocated, and that is really a determining factor. I think I'm going to give you a couple examples here just to drive it home, because this is a new concept for everybody, or for a lot of people out there. Everybody has felt the need for it and sensed the need for it. And I think it's really important to simplify it down. So let's look at how this can matter, because it truly is where this becomes important. You can literally have two facilities side by side with the exact same PUE. Both are equally efficient in how they use energy overall. But then interestingly enough, these two data centers may not have the same ability to support compute. So in this example, what I'm trying to show here is that one of them allocates more of its provision power to cooling and overhead. And that's very, very typical of our data centers that are 3 or 4 years old. The other one allocates more towards compute, kind of the goal of what we're after here. And so, but PUE does not capture this difference. So PUE was never intended to reveal these kind of differences, and PCE will do that. And that's where PCE actually lives. Kind of the same type scenario, but I think it's an easier way to look at where we're moving with this. Because where it matters is where when we are looking at chasing power, but also looking at our current assets. So in this example, we can see that both facilities still have the same power, same total power provision to come in. And neither one has gained more megawatts, but the difference is how that power is allocated. So the considered infrastructure here, the design has changed how much becomes provisioned and potentially usable for compute. We can see in this example what I've shown you here is if we move into a facility, an existing facility that was built with the legacy air cooling, the most dominant type of cooling system out there for the last 20 years, we show that only 40% of the available provision power is provisioned for compute. And the legacy air cooling, what that takes in, and it's very important to stress the term provisioned here, because the legacy air cooling may only be occupying 10, 20, 30% of the actual power, but 40% must be provisioned to it for peak loads, peak demand, inefficiencies, things like that, which means that we can only provision 40% for compute. We move towards the more aggressive, even today's entry immersion cooling, we can now say, hey, the provision allocation only needs to be 50%, even at the highest stress loads, which means we can now, overall, we can now reroute and re-provision 65% of the total power, same power coming into the facility, but we can now change that into the compute. So very quickly then PCE, it looks like it's an inversion of PUE, but it is clearly not, because the key term here is provisioned. So PCE has been introduced to the market and it's, by the way, it's currently supported by Uptime Institute. It's in the final review stage at OCP. In fact, the global release to PCE was just signed recently, so it is available for everybody to own. It is the upcoming metric for this. It was recently published in the Amazon bestseller book called Green Data, but it's not yet been fully introduced into the greater data center design market. That's going to be happening later this year and throughout 2027. And PCE is a very structural metric. What it does is basically evaluate how the actual provision power is allocated. What it does not measure, and what it's not intended to measure, is efficiency. And it doesn't measure server performance, because that's when you get into flexible loads and variable loads. And I'll tell you, initially when PCE was first brought to OCP, this was the point of contention significantly, because we have different ratings on plates, or also different on nameplates of servers, but also different inference schedules and peaks, and it became too much of a variable. So the standardization became on the provision portion, actually revealing what kind of power could be found in our existing assets. So in other words, changing servers does not change the PCE. Only infrastructure design changes PCE. And it will never measure ROI. It can lead to return on power invested, but not the actual ROI. So it's never been intended for efficiency or performance or ROI. And that's the key distinction in all of this. So again, PCE is going to measure the power allocation. The total provision facility power is fixed, and it's within a defined boundary. And that's the point of everything here. So we're talking about the chase towards power, and the power is not available, and it's extending the timelines to unsustainable amounts. So PCE is intended to focus on what provision power do our existing facilities already have, and also for the new greenfield facilities. That power is structurally allocated to provisioned cooling systems, provisioned electrical losses, provisioned auxiliary systems, and then ultimately provisioned IT compute capacity. And PCE is going to measure the proportion of that total provisioned power that is allocated to compute. It's a structural review of infrastructure design. It's not an operational measurement. Key to this is cooling determines the allocation. So we'll kind of flip back to what we were looking at before under the PUE lens, and let's flip that to the PCE lens. And it's an inversion to a degree, but we always have to put in that stipulation of provisioning. So when we were looking at PUE, and the lower your PUE number, the more efficient that the data center is considered. PCE is going to work the opposite. So a 1.0 would equal 100% effective use of power provision to the facility, to power provision to compute. Currently, we don't have any way of achieving a 1.0, but the closer we get to that 1.0, the more effective we are at finding existing power rather than chasing future power. So again, we look at before the legacy air cooling system, that would have had a PCE rating of 8.4. And we're finding traditionally that's what we see out there as we're meeting with more and more of the hyperscaler, and actually the enterprise owners have a key interest level into this. So do the investors and the utilities. A 0.4 to a 0.5 is pretty common out there. What we're looking at is when we change the strategy and we replace the existing air cooling with liquid cooling technologies at a higher delta T, and higher delta T is an important portion of this. We can drive PCEs. This is a very conservative example, but we can see a PCE of 0.65. So that's over a 60% increase in PCE, or power that's provisioned to the facility that's now able to be provisioned to compute. That's significant. That is transitional change. That's potential there. And so we look at the heat rejection limits towards compute. It's really important. So let's look at the new drive to 45C from the Vera Rubin. AI increases the density, and that density increases the heat. So obviously, it's apparent the heat rejection becomes the limiting factor now, not the server, not the racks, it's actually heat. When we look at that and how that all works out, the higher the temperature, the lower the overhead. And that is such an important factor that I think even in the last session, we didn't discuss this. And this is where I think a critical pressure point exists in the industry, but there's no focus, or not enough focus being made on that. Thank goodness NVIDIA announced the 45C, but we've done testing, and multiple companies have done testing up to 55 and even 60C for the inlet temperature for the chips. What that does is dynamically release a lot of energy consumption, because we can begin to eliminate compressors on data centers. If we can start eliminating compressors on data centers globally, we release a new potential power in the ranges of anywhere from 40 to 60% power gain with our existing structures. That's a dynamic transitional difference that we can see there. Lower cooling demand means more power available for compute. That's basically what it is. So the delta T it changes everything. So it needs to be considered in here when we're talking about this new metric. We know that the higher delta T improves heat transfer. Better heat transfer reduces system load, and then this directly impacts power allocation. So really, it's water usage, it's noise, grid strain. These definitely impact the permitting, and then the community acceptance, which determines whether a project gets built. And the infrastructure defines the ultimate outcome of all of this. So undoubtedly, different architectures are going to require different levels of cooling, no doubt about that. And the power to compute focal point, that needs to be reminded, that actual focal point needs to be reminded on how significantly that simple fact directly changes how power is allocated. Infrastructure design determines the PCE. The PCE can reveal the power we already have. So that's really the entire focus of introducing PCE to the market and why it has gained so much traction so quickly. Again, it's been published by Uptime already, published in Greener Data, will soon be, we assume, I don't see any reason it won't be, published by OCP as a new metric to be utilized out there. So, the real reason is because that the struggle that we're seeing out there, it's very real. Power is the constraint. And the fact is that power allocation determines that usable compute capacity, which is what we're all after. It sounds really simple and it sounds very apparent and obvious, but it's not being utilized. So that's why it needed to be defined. And cooling itself drives this allocation. Infrastructure, let's just say infrastructure is going to connect all of it. Thinking in these terms and in this order, it opens a whole new potential. It opens new realities. So the fact is, as we're chasing power, the greenfield itself is slowing and demand is not. Communities are pushing back. Legislators are becoming more involved. And to a degree, it's very rare that I would say this, but thank goodness legislators are becoming more involved. But interconnection timelines continue to extend. At the same time, dynamically, it's opposed because AI demand is accelerating while interconnection timelines continue to extend. And the compute density is also increasing. Timelines are compressing, almost collapsing to a degree. And this has created a complete fundamental mismatch in our market. The compute demand, it cannot wait. So, a quick review there. The power is taking years to deploy. We just spent quite a bit of time talking about that in the last discussion. And it's very apparent, very true, and very detrimental. Compute demand is immediate, yet power takes years to deploy. Fact is that's not just a capacity issue, so it's also a timing issue, and all of this plays together. Ultimately, what we argue here is that we need to stop chasing the power and start using it better. Yet the industry response has been consistent. We chase new power, to the extent that we're even hearing the term bragawatts, right? Every expo that we go to, we're chasing the new gigawatt here, or 3 new gigawatts in 3 years, and it's taking us 15 years to get to 2 gigawatts. And I've heard that term bragawatts bannered around, and I'm not comfortable with the term, but it does kind of shine a spotlight onto the actual real problem there. But the faster path and the smarter path towards these additional megawatts and gigawatts is obviously to use the power that we already have and to use it more effectively. Which drives us obviously to how to unlock the compute in existing facilities. And these, by the way, these are not theoretical ideas. These are real engineering levers. We can, and I'll even take that one step further and say we must increase the delta T. We can and must increase the temperature differential. By doing so, we need to design to a reduced cooling allocation. And then the ultimate result of that, the immediate result of that, is that we convert that into compute capacity with the power we already have. So instead of chasing, we harvest. And it's a dynamic change. So this is where liquid cooling and the higher chip inlet temperatures fit. It's not just about improving efficiency. It's about driving the shift towards allocation, reduced cooling share, and increasing compute capacity within the exact same power envelope. There are a lot of approaches out there, different immersion cooling portions out there, obviously direct to chip. There's the evolution that we've seen from several different, I posted ours up here because I had the pictures handed at the last minute, but there are many ways to go into the facilities nowadays and actually free up real estate with liquid cooling without that much of an infrastructure change. Certainly we need the piping, but we get to eliminate compressors and free up tons of power so we can shrink the footprint of the existing CPUs, create brand new footprint within the existing walls for the GPUs, and eliminate compressors. It's all there. We know how to do that. And as we increase temperatures, we also increase the dynamics for the repurposing of the energy. So if you have an interest in the PCE, which you should, I think everyone here, I'd encourage you to join us into your thought leadership process, because it will become the very real metric within the next 6 to 8 months, 12 months, whatever that is. But it is time. It is transformative. It is powerful, and it's real. It's there for us. And I would say it's almost incumbent upon us to start looking at things through the different lens. Ultimately, I think, just kind of end it with the constraint is no longer how much power you can get, it's how much of that power you can actually use for compute. So that kind of opens up whatever time we have left here, which I think is very little, for any questions.
Yeah, perfect. I'm going to take it away, Paul. Not a problem. I see we've got some questions in the Q&A. I'm just going to quickly open up now. First one. So you mentioned so that there's no metrics measured allocation and that there is a PCE come in. Where does PCE come in? Sorry. How can we fit the PCE in with the CUE, WUE, etc., as well as PUE?
I think they all fit together, and I think they intertwine beautifully. So PCE is the metric that's missing for allocation. And for us, we're truly focused on how do we use the existing power in a much, much better way? How do we reallocate that towards compute? WUE, CUE, IUE, PUE, they all have a very real place in this. All of them need to be combined towards the correct future focus on utilizing and actually being stewards of the power that we have available.
Perfect. So one more question we got from the Q&A chat. So if air and liquid cooling are living under the same quote unquote roof, how are you seeing operators handle the skills gap in their maintenance teams, for instance? And is it a case of retraining existing staff potentially? Or are we looking at an entirely new breed of data center technicians?
No, I don't think we need to do that at all. And I think I'm gonna flip that argument a little bit, and talk about the world is concerned right now about AI replacing their jobs. What we're showing here is no, AI
Plumbers,
is going to create.
electricians.
Yeah, exactly. We need more higher skills. And so
Yeah,
I think it's a great resolution for that.
perfect. And there's one more question here I can see. So the legacy sites that we want to retrofit potentially for AI, it's a very big topic right now in the industry. Is it actually viable to bring high density cooling into the older facilities, or are we just reaching a point where the AI era requires a totally completely new slate for a new build?
Well, I could say both. I think what we focus on first is the powered and the permitted. Let's focus on that. Now, if you want to bulldoze what's there and go from scratch, that's fine. You can certainly do that, but I don't think the market will tolerate that because that doesn't answer the speed to market question. The demand for compute is there now. I think what we need to look at is CPUs aren't dead and won't be dead. There's an enormous market and always will be for the CPU processing, higher density CPU. The market for GPU and AI is misunderstood. And right now it's actually on the user rate, it's about an 80-20, and 80% is still CPU. So we need to look at the existing CPU facilities, increase the density, increase the technology, increase the speed of
Mm.
those, but shrink the footprint. And within the new available space, now we add GPUs. So our entire hyperscale market, it's very difficult to do at co-location because we don't know who pulls the strings ultimately in co-location. But the enterprise markets are just starving for this. They need to implement some AI, but they don't want all AI. They need their CPU, their basic data, but they need it at a higher escalated rate. So it's a beautiful retrofit market. Stop scrapping and start retrofitting.
One more question on my side, a couple more, sorry. So with your water usage shifting from the environmental metrics to a more politically sensitive issue, how is the reality changing the actual cooling technology decisions you see being made on the ground today?
Oh, it's wonderful. It is absolutely beautiful. I think WUE should be 0.0 all the time. I mean, with liquid cooling, when we can increase the chip temperature, we can eliminate compressors. We can do fully closed loop. We don't need cooling towers anymore. We can stop using the water other than the initial fill. To the degree where when we get the temperatures up there high enough, we can also stop using glycol. We can really use clean water without having to wastewater. And I think the communities are right to be outraged about that because we need to be pushing again the chip temperatures and the cooling technologies and say we have the technology, we have the ability, but we're not investing in it at that investment level. So I think that's where the pressure needs to be.
Perfect, perfect. So going back to the liquid and air cooling context, so as they are coexisting, how do operators design for both without creating a massive operational headache or stranded capacity moving forwards for the future?
I think that's incumbent upon your cooling design. And it's not difficult. It's not difficult at all. Um, but there are multiple technologies. It's very difficult to get into all of them right now. But we can transfer some of that heat waste into cooling again. We can transfer it into new energy. There's so many things that we can do as we start to increase the temperatures and increase the delta T's. It's there for us. We know how to do this.
Perfect. Then we got one more Q&A question that's popped up. So from the audience. So if PCE becomes the new gold standard metric, what does that mean for the supply chain in question? Will the operators start demanding deeper performance data from the chips and server manufacturers that they never used to ask for before?
Well, that PCE is not going to impact that directly. So PCE really, the intent of it is, first of all, not to become the only gold standard, is to work in unison with the other standards. But what it
Mm,
does is PCE allows us to put more provision power towards compute. That's where PCE stops. What the chip manufacturers do, what the server manufacturers do, what inference does, when agentic AI now starts to level load our server capacity, that's all market demand. PCE just allows us to provision the existing power that we have towards that new market demand and higher densities.
perfect. And there's one more question that James has asked us. So within the next 24 months, if an operator is still relying solely on traditional air cooling methods, are they already a yesterday facility, or is there still a long-term play for those sorts of models in the AI world?
Oh, it's not. It's such a wonderful question because it's not just they are actually reviewed as dead assets on a balance sheet in
Yeah.
many industries, and I think that's just outrageous.
They still
Everybody
have more
look.
functionality, more long-term longevity, if anything.
It's amazing, but they're considered dead assets, and we're just chasing greenfield data centers, but there's no power there. The power
Mm,
is limiting. The communities are protesting, but for some reason, the market is not yet focused back on, my gosh, we already have the power and we already have the permits. Let's be smarter about how we use it. Well, the communities are going to support that. So much of the pressure goes away. It's one of those things that is so obvious. You look at PCE and you say, well, that's stupid. Why didn't we think of that yesterday? Why didn't we implement that yesterday? We have to do this.
perfect. I think one more question just from my side regarding PCE. So you've made a very compelling case for PCE, 100%. Is the new critical, that will be the new critical metric, of course. Is the time for the industry to officially move away from PUE in favor of measuring how much power actually reaches the chip itself?
As far as prioritization, I would say PCE should start becoming first, both on Greenfield and your existing data centers, your legacy data centers. Where we're seeing a significant amount of traction on PCE is the investors. Thank goodness. When we created the PCE metric, it was because there was a void and we needed to look at this. And
Sure.
it is not for AirSys. This is for all of everybody who is interested in the liquid cooling and increasing the efficiency and effectiveness of how we're utilizing our power. It is everybody's to use. The fact that the investors are grabbing onto it first really just amplifies the dynamics of it and the speed of it. So it's coming very quickly. When Uptime released it, that was a big momentum shift. OCP has been grabbing it for a while. We just went through, everybody signed all the releases so that everybody owns PCE. It's anybody's who wants to use it. And OCP will be doing final review here within the next month or two.
Perfect. Fantastic. Those are all the questions I have for you today, Paul. Thank you so much for your time. I really appreciate it.
Hey, what a pleasure to be on. Thanks so much. And this is a phenomenal broadcast that you're doing here. I'm learning so much.
Likewise, I'm learning just as much as you.
Yeah, yeah. Okay. Have a great day.
Thank you so much. See you soon, Paul. Thank you.